Hello, everybody. This is part 14, the first chunk of the lecture on mathematics and signal processing. We're in the middle of using the Fourier inversion theorem to derive a number of results to show that the forward and the inverse Fourier transform are really very symmetric with respect to each other. So far, we have only the convolution theorem showing that convolution goes to pointwise multiplication. But of course, in a symmetric situation, you expect pointwise multiplication goes to convolution, and that there is some invariant. There are a couple of invariant spaces or so. So because I have had a serious typo last session, I would like to correct this and resume at page 91 of the current version of the script that will change during the time, of course. So we were starting from the fundamental relationship for the Fourier transform, and that can be written as g hat integrated against f is the same as g integrated against f hat. So you have two variables, you take the product function f of x times g of s, you integrate it against the character e to the minus 2 pi I scalar product of x with s, and you have a double integral, and if you evaluate it in one or the other way, you get exactly the left and the right hand side of this. Now, it's really fundamental, as we will see also several times in the future, but it's used to prove the Fourier inversion theorem by saying, well, if this is true for arbitrary functions, we can insert functions such that we can pick out the value f on the left-hand side, where at the same time we do some integration on the right-hand side. Now, what we have to do is very simple. We would like to have some object g hat which picks out the value f at the point t. So you think of a Dirac sequence at the point t. Now, how do we get this on the Fourier transform side? We do some dilation of some nice function that we know the Fourier transform, like the delta function. We know the Fourier transform is sinc square, which is integrable. Then we stretch it, and then we modulate it, because on the Fourier transform side, that's giving exactly something which is nice, just integrable, not compactly supported, but nice in L1. You compress it, you get this Dirac sequence, but that should be not at an arbitrary position, but at position t. And so by taking limits, we come out with the right thing. The only problem that we had, and I really realized that this is a delicate point in the argumentation, is that the factor that we get by pulling out this on the other side is this L1 norm of the sinc square function, or the value of the Fourier transform of the delta. And that is clearly some positive number, but we have to determine what it is. Now, without repeating the argument, we get on the left-hand side that by using this fundamental relationship and taking a limit, as I was doing it in the abstract scheme, we pick out the value of this inverse Fourier transform of f hat, and our assumption was f hat is integrable. So this is ordinary Fourier transform at the point t, but multiplied with some positive number. Going to the other side, we see that we get the Fourier transform, we get an expression which we can read as the Fourier transform applied to f hat. And that was the typo, which was really disturbing last time. But with the argument minus s, therefore we say in the flipped version. So this is a function. Recall, f hat is integrable. Fourier transform f hat is a function. We flip that function, and it's evaluated at the point t. Now this is true for any value t. Therefore, we can say that the inverse Fourier transform up to the factor gamma, which I move to the other side, is just forward Fourier transform combined with a flip. So this explains very much that also the inverse Fourier transform maps convolution into pointwise multiplication, which of course is the same as saying under appropriate conditions, we are working usually now with L1 intersected FL1, we turn pointwise multiplication into convolution, and everything is very symmetric, and that's really one of the goals that we have. Now, how can we determine the vector gamma? You can take, in principle, any function where you can compute the Fourier transform and the Fourier transform of the Fourier transform, so the double Fourier transform, But there are very few examples where you can do it, and the best example would be the Gauss function. So the density of the normalized Gauss function, I still haven't corrected this pi here. So it's exponential function minus pi x squared. This means, of course, that the Gauss function, clearly exponential function at 0 is 0, is the same as the Fourier transform, which is the same as the integral, which of course is what you can learn in the probability course, where you determine the density of the normal distribution, and it has to be integral 1 to have to be a probability measure. Now, this is kind of a correction of what we had before, and the consequence is the observation that L1 intersected the Fourier algebra. We do not have to distinguish between the L1 functions which have a Fourier transform in L1, or the functions which are in L1 and are also the Fourier transform of some other function, because of course any function can be obtained as a Fourier transform of its own Fourier transform up to the flip. And we have observed that the flip can be done before or after the Fourier transform. So it's a nice formula to think that double Fourier transform is flip operator. Flip of flip is, of course, original position. So the Fourier transform going in this way is the identity. So the first power of this is the identity. Now, I would like to use that once more to recall that we are using certain function spaces. So I'm sharing another screen now. And we have started to use these amalgam spaces. So it was a very important property very early on that bounded measures can be cut into pieces. These mu psi I are the local pieces. More or less you can think of these are the mass that you have in a bin of a histogram. So it's from n to n plus 1 to n plus 2, n plus 3 or so. And the mu psi add up to the total measure, and the sum was absolutely convergent. Now, if you do the same thing inside of C0, you can take a function in C0, cut it into pieces. So what you really do is you're doing an upper Riemannian sum, where the steps are going from n to n plus 1, and you're asking that this is summable. So essentially, I will talk about this so-called Wiener algebra as something which is locally with a subnorm, globally with an summability. So little L1 is the sequence space of all integers, of all sequences indexed by the integers or by the lattice set D, which have a total finite sum. So that's quite easy. But this is a much smaller space compared to C0. So we have seen, for example, the sinc function is decaying at infinity as any Fourier transform, but it is not at all integrable or so. So whereas here, you even can do a Riemann integration. So you may remember the Riemann integrals are first defined for finite intervals. So you are saying, I understand what the integral from minus 10 to plus 10 is. And then you take the limit, limit of the proper Riemann integrals. Now on this Wiener algebra, you could do infinite Riemannian sums. So you take the maxima, the minima on each interval, and you would also find that that would converge into an integral, which is either the same as the Lebesgue integral for such simple functions, or the indefinite Riemann integral, or something that you can do only on this space or so. So if I compare the spaces that we have at this moment, it's C0, the very basic function space. It's L1, and you have some functions which are, of course, not continuous, but integrable, of course. And then we have the Wiener algebra, and I was using this turquoise light blue object with the argumentation that locally and in the middle of the picture, so kind of in this area, I would say it's behaving like the continuous function. Globally, you see here I have L1. The global behavior of L1 is the same as the global behavior of bounded measures. Therefore, I used part of the symbol here. So this kind of stretched hexagon is my symbol of the Wiener algebra. In between, I had slightly different models for this. I mean, different dilation parameters or deformations. But in the final stage now, I'm using this normalization because I would like to show that if we take those functions which have a Fourier transform in Wiener's algebra and are in the Wiener algebra themselves, they're a very nice Fourier invariant subspace. So this magenta hexagonal, it's now squeezed in the other direction, is just a rotation by 90 degrees. So I'm using symbols for spaces, and their Fourier image is then the same, rotated by 90 degrees. Now, if you take the light blue hexagon, intersected with the other hexagon, the rotated hexagon, you get exactly this square. So I didn't color it, didn't fill the color, but that is what you should think of the space, which is nice, decent Riemann integrable function with a Fourier transform, which are Riemann integrable. Now, I think it's wasting time in an engineering course, but I would say this would be my space if you would do a complete down-to-earth presentation of the Fourier inversion theorem. You wouldn't use abstract functional analytic arguments, but you would go on, prove it for Riemann, using only Riemann integrals and making a lot of estimates. That would be the right domain for the Fourier inversion theorem. But it's also a good domain for what we will see is the Poisson summation formula. I will come to this not today, but later on. Now, inside this space, we have, because every function in the Fourier algebra, every function which is the Fourier transform of some L1 function is a continuous function vanishing at infinity. And therefore, I use the symbol FL1 locally. So within the Fourier algebra, there are certain elements which can be written as absolutely sums of their pieces. Now here it's important that the partition of unity is not the sharp cutoff that we could use for continuous functions. Here you're measuring sup norms and you're cutting and taking sup over intervals. But here, if you multiply a function in the Fourier algebra with the indicator function, let's say from 0 to 1, you get a discontinuous function. It's not in the Fourier algebra. You cannot measure it. Therefore, it's so important to have these bupus, these bounded partitions of unity, for example, using the triangular function, or I prefer the trapezoidal function, because it gives you the spirit that essentially on an interval, let's say from 0.1 to 0.9, I'm really measuring the part of the original function. In the transition around the integers, I have a slope, just a linear slope. It's good enough for the definition of this space or so. And the indication here is also that the round object allows not only rotation by 90 degrees, but arbitrary angle that will be related to the fractional Fourier transform. Probably we will not be able to cover this. But still, you see there are a lot of spaces, and the goal is not to make things extremely complicated, but to make it as simple as possible. So we have already seen that we can do things for simple functions like continuous functions with compact support, but unfortunately their Fourier transform cannot be so nice, so they cannot have compact support. That's why you need other spaces. But we will work with this object, which I call a Banach-Gelfand triple. So you have to learn that what is by construction the Wiener amalgam space, which has locally the Fourier algebra and globally L1. And we will see this is more or less functions which on each interval, if you take those pieces as periodic functions, you continue them, they have harmless, absolutely convergent Fourier series. So these are the functions that people in Fourier analysis would say, oh, these are nice. The Fourier series is converging at every point or so. And now what we are doing is we're gluing these local pieces together, but in an L1 fashion. Now, I just claim that this is a nice space. We also have not done much about L2, but we have seen Plancherel is a consequence of the inversion theorem, so you can extend the ordinary Fourier transform from a dense subspace to the whole space, and this is a unitary mapping, a unitary automorphism. But it still doesn't allow you to show that you can invert the Fourier transform of the Dirac delta. You know, Dirac delta is identity for convolution. Therefore, the Fourier transform must be identity for pointwise multiplication. So very simple formula, which you can prove in half a line. Fourier transform, Fourier tilde transform of the Dirac measure, which is a harmless bounded measure, is constant 1. So you expect, of course, that the inverse Fourier transform of constant 1 should be back Dirac. But you cannot do it because it's not in L1, not in L2, it's not even a function. So we have a quite nasty asymmetry using these classical terms L1 and so, whereas here, everything is fine. So we only have to go and find a way to understand the good properties of S0 and more or less jump directly to the dual space and define the Fourier transform or the extended Fourier transform on a space which I meanwhile call the space of mild distribution. And we will have many different ways to characterize them. So sometimes I'm even saying what you hear now is my voice, which is transmitted in a digital way. So there were some linear measurements. We could compute a spectrogram. So this is kind of the largest space of objects where you can have a spectrogram, a bounded spectrogram or so. So this is the goal, and that's why I wanted to show this to you. Maybe I also remind you a little bit about the more classical picture that we have on page 1 of this script. So this is the universe that will be good for all of our tasks. We have started, or classical Fourier analysis starts with the blue object, the L1 space, going on with FL1. Here the light blue is a different one. It's the elements that we used for the inversion theorem. And the white one is Wiener algebra with Wiener Fourier transform. And so you see how they are all intermingled. There are continuous functions which decay, but do they have a Fourier transform? And the answer is yes, of course. They are functions which are objects in the big space because the rotated C0 space, sometimes called the space of pseudo functions, is just inside this big circle. So all these things are okay. And above all, Dirac combs or Shah distributions will be part of this big universe. Therefore, all the periodic discrete signals, even the finite discrete objects are all in this. And this is kind of why we are continuing to work with this fancy or not so popular, so far not so popular function spaces. So I'm returning now to the extended slide to see. I'm not sure. No, this is the wrong. Yeah, here it is. So, okay, so I do not repeat what I maybe I just very quickly. I recall that the key point or the delicate technical point, which we did in all details after the Riemann-Lebesgue lemma, is the inversion theorem from which we were applying the Plaucher theorem. And I was giving an indication here in this text. If you would choose to take the 2 pi I mean, avoid the 2 pi in the exponent, then you would get it in the inversion theorem. You could try, and you would get it in the convolution theorem. At least in one direction, you would have a problem. You can have the Shannon sampling theorem, which we will see very soon, and you would have a very nasty expression. The Nyquist rate would not be in a very natural way. So 2 pi pops up in 5 different places. Also, the Gauss function wouldn't be Fourier invariant. But if you see formulas which are maybe saying, well, we would like to save Plaucher to make Plaucher isometric, then we put a 1 over 2 pi, square root of 1 over 2 pi, maybe times to the exponents d in the multidimensional setting, then everything would be okay for Plaucher, but still the convolution theorems wouldn't look nice. The sampling theorem wouldn't look nice. So a book which is very rich is the book of Putz and Nessel from 71, and he uses this terminology. So he's safe for the proof of Plaucher or so, but not for what we want to do. Now, I was also indicating, and I'm really doing this now quickly, that the Fourier algebra, the concept Fourier algebra is justified because we know that L1 as a subalgebra of the bounded measures with respect to convolution is a Banach algebra, and by transfer of structure, convolution goes to pointwise multiplication, or you can say composition of linear systems which are invariant corresponds to pointwise multiplication on the Fourier transform side, so multiplication of transfer functions. So therefore we have this pointwise Banach algebra property, and we also have verified that you can convolve elements in the Fourier algebra and you're staying in the Fourier algebra. And intuitively, the last line of this argument I just indicated back is very simple, because we're now free to move back and forth. We would say, oh, can we convolve a function named f hat in the Fourier algebra with a bounded measure? And the answer is yes. Let's go to the Fourier transform side. Well, of course, to start with, you take everything, the f and the f hat in L1 with intersected Fourier algebra, because then switching is no problem. So you say, oh yes, this is going is the same on the L1 norm on the other side. But on the Fourier transform side, multiplying with the bounded continuous function is harmless, and therefore you can rewrite it. You estimate the Fourier Stieltjes transform of mu hat by the measure norm, and you go back from f in L1 to the f hat norm in the Fourier algebra norm. So multiplication of an element in L1 by some bounded function named mu hat is harmless, but we will use this fact also further. So I'm skipping now further identification. Here again, you have this formula. But I would like to mention, I think it's a very nice mathematical statement, but we will not need it. Maybe two parts of the statement. I will maybe type a few statements, the easy ones I will type, and the rest is not so important. So how can you recognize whether function is in C0 is in the Fourier algebra? So it's about the question of, well, how are the Fourier algebra and C0 related? And we have seen that the Riemann-Lebesgue lemma tells us all the elements in the Fourier algebra are in C0. We have also argued that, for example, triangular functions appear in the Fourier algebra, and therefore piecewise linear functions with compact support are in the Fourier algebra. We can approximate any continuous function with compact support, therefore any L1 function. So in this way, we can find different ways. Maybe that wasn't a formally correct argument, but it's easy to find out, let's say, in this way, that the Fourier algebra is dense inside. But it's also a proper subspace. Also, that would take a couple of minutes to explain, but it's possible to find functions which have L1 norm 1, so which have highly oscillatory terms, so that their Fourier transform is having a big support, very large stretched, but very flat. So the sup norm can be arbitrarily small, even if the function is normalized. So that's an interesting observation. So people can ask, well, if you give me a function in C0, how can I recognize it? And the answer, which I would call a formal answer, is just this one. If and only it can be written as a convolution product of two L2 functions. So maybe I should write down this it's almost at the level of a theorem, or at least proposition. If you convolve two L2 functions, you easily recognize that it means by Plancherel that you're doing a pointwise product of two L2 functions. But there is the famous Cauchy-Schwarz inequality that tells us this is in L1. So on the Fourier transform, such a convolution product is in L1, which means taking everything back by Plancherel, that you're getting inside FL1. Now, on the other hand, the question is, how can you get a factorization? I claim there's equality. And I would like just to mention, the idea is that if you give me a function in L1, then the square root of the function is in L2, because we all know that the square root squared is in L1 is the original function, and that was supposed to be L1. And next step, you get all the L2 functions in this way. So a function is in L2 if and only if it is the square root of an L1 function. I mean, every function positive is the square root of f squared, so we are back. So how can you split it into a pointwise product? Well, take the square root. And how can you split it in the convolution product? Well, take the Plaucherel inverse transform. Now, this is easy for positive functions, but if you have a complex valued function, you have to split into the absolute value, which is good, and the rest is the absolute value plus the phase factor in order to get this. This is not important because in reality, it's more or less impossible to show that the function is not representable in this way, because if you look at the right-hand side, there are kind of infinitely many positions, and to say it's absolutely impossible to write it in such a way is not easier than proving directly that, well, let's take the Fourier transform of the guy here, or the inverse Fourier transform formally, and check whether this is integrable. So clearly, yeah, this is very helpful for theoretical purposes, but not so relevant for applications. So I was already indicating, and that's an example of what we are going for with the dual space with S0 prime, that we would like to show that the inverse Fourier transform, well, if it's a function, we're not sure, that as a function of t, it should be written as taking the inverse Fourier formula, integral over the real line, constant 1 as a function of s, so just the value 1 times e to the 2 pi s. So that's what you find in quite a few engineering books. And you also find that, well, this is delta 0 at t. And an argument which I cannot accept, because the Dirac functional is a measure, it's a distribution, but it's not a function. The kind of intuitive argument to justify this is you're saying, well, if this exponent, well, t is different from 0, you're having an oscillatory term, cosine and sine, and the integral will, over the whole real line, the positive and negative parts cancel out, so you get 0. Okay, so some function which is 0 everywhere except, well, for t equal 0, this is constant 1, and you're saying, hey, that's great. Its integral is plus infinity, and that's the definition of the Dirac. And my critical comment at this place, you hear it probably too often, is, well, why isn't it 3 times infinity? Why is exactly 1? Is it wishful thinking or so? So kind of, we will see that abstract Fourier transform helps you to do this. Now, I don't go into the details of the proof of the Plaucherel theorem. I just say that it's obtained by starting from the dense subspace of L2. I'm not given a formal definition even of L2, but I say we have a nice Fourier invariant space, but we can impose the L2 norm. We can take this integral, and you know the function f is integrable, and it's also in the Fourier algebra, therefore it's bounded and continuous. So you can say I multiply the f with the conjugate of f, which is a bounded continuous function. So this integral is finite. The same is true on the Fourier transform side. So the two expressions are well defined, and I only have to show that they're equal under the given circumstances. Now we go back, and that's why it's really the fundamental theorem, go back to this relationship, and we would like to have, well, if you take a general scalar product, you will say I have scalar product of f with h. That means I should integrate f of t against h t conjugate. You see here, I'm trying to make this choice. I would like to have this g hat here, to be h hat. And then we will see what happens on the Fourier transform side. And this is maybe something I would say that's something that you should be able to reproduce after exercising it a little bit. Kind of, how can I get the Plaucherel theorem, or this isometric property, and then the Plaucherel theorem from the fundamental relationship. So idea, g hat should be like H conjugate. Therefore, of course, applying the inverse Fourier transform, so to get back from G hat to G, we have to take the inverse Fourier transform of H hat. Now, we have seen, and that's the formula that was the correct formula now, that the inverse Fourier transform can be viewed as applying the forward Fourier transform and then a flip operator. So we leave the H bar as an argument, apply the forward Fourier transform and then the flip. But then we have seen a rule that how these involutions are changing. So the star involution, which is the combination of flip with conjugation, goes to conjugation in the sense of complex valued functions. Because the inverse Fourier transform has the same property, also the forward transform moves the H conjugate into H Fourier transform star. So we can say, okay, now I'm writing, instead of F, I'm writing H hat. So this is applying first the Fourier transform and then doing the involution star. That's what happens inside the square brackets. And then we do the flip operator. But I told you that star is conjugation combined with flip. So we have two flip operators and only the conjugation remains. So this means that if we start here with something which is the scalar product of F with H, we get on the right-hand side, on this side here, F hat against H hat conjugate, which is of course the scalar products over the S variable in this. Now we can specialize it and say, well, what if we take F equals H? Then of course the scalar product of F by itself, which is F L2 norm squared, is the same as F hat L2 norm squared. But both expressions are positive, so we take the square root of this natural equation, which you get from here, and you have the isometric property. The rest I would say I leave it to you, or we can do it later on. It's just abstract nonsense in the sense that you're saying now we are approximating the functions by these elements from the dense subspace. We take limits in the F and the G variable, and we get either directly first that we have a scalar product preserving mapping of L2 into L2. The extension is also having this property. It's also isometric. You have to verify that it's not only an embedding, but it's also a surjective embedding. So if somebody says, well, can I reach every L2 function? Well, you approximate it by functions in this space L1, FL1. You go back and say, well, the approximating elements can be moved on the other side, and because everything is isometric, you can easily extend this isometry. So Clojurel is an extremely strong theorem, and we have already more or less done it. Now, I was already telling you that we will do the construction for certain spaces, and the two examples of such homogeneous Banach algebras are C0, which is the easiest and prototype, and the Fourier algebra. I don't repeat the properties. We're going to use them, and we will see, rather spend time on explaining the details. I also was kind of indicating already, and would like to recall it, that the Fourier transform, the Fourier algebra is satisfying all these properties. So essentially you can say, well, I will need certain properties of the Fourier algebra, but instead of using them ad hoc in subsequent proof, I'm just making a list of all these properties, and I'm only using this from the formal list. Okay, so what is the idea of the amalgamation? We produce the subspace of all the elements which are absolutely convergent if you split them into pieces. So since A has to be a subalgebra of C0, it's really a pointwise decomposition. So in the pointwise sense, I mean, there are only finitely many contributions for every point. So f of x is pointwise in a very ordinary sense, the sum of the values of the local pieces. So at every point, even on any interval, this sum is nicely uniformly convergent. So there is no convergence problem. The assumption that I made is that this psi k have to be a bounded partition of unity, and boundedness now suddenly refers to the boundedness in the algebra. But as you know, we can take the triangular function or trapezoidal functions. They have Fourier transforms which are integrable. So they are very nice bupus for my application. You can take them even with higher smoothness than you have, let's say, cubic B-splines or so. So there are plenty of such things. But at first sight, we have the problem that this may depend on the choice of the partition of unity. And the answer is, this is a harmless problem. And I was probably in the script you have, or still the proof that you can show independence of the concrete partition of unity, but it can be obtained from the more general atomic decomposition, which I also have done already. So you split a function in A into an absolutely convergent sums. Each of them is living in some small ball, or ball kind of even a big ball, but of a fixed maximal radius. So if potentially infinitely many atoms, their norms have to be summable. So we talk about absolutely convergent sums in A, and their support should be uniformly controlled by some radius R. And this is another characterization. And you remember I was giving you this picture of overlapping balls. So we are finitely many balls which are counted in this way. And we get an enormous equivalence. And so the point is now, and that's I think what I would like to argue, is with this characterization we can prove a lot of things. So first I will go through the properties and then I will try to make the argument. One is that the compactly supported elements are a dense subspace or so. Then the translation operators, they may not be isometric in the original sense. So with this fixed bupu, because if you shift a bupu, it's maybe not exactly compatible with the original one, but with the atomic representation, this is no problem. Translation is continuous in the space. It's also possible to have a Banach algebra structure with respect to pointwise multiplication, or you can take an algebra which is dilation invariant. Again, C0 is fine, Fourier algebra is fine. And you can take actually both dilation operators, the D-row or the S0 operator, and then the same is true for the new space or so. So maybe I'm trying to explain now how to prove various things and why I'm choosing certain arguments. I'm not going through all the details, but I would like to give you a background on why I'm choosing certain arguments. And if you find some gap in my argumentation in the written version, please let me know, even if the gap is only something in the gap in your first understanding. Okay, so how can you prove completeness? Now, an important observation is, or practical experience is, if you want to know completeness, you have to only show that absolutely convergent sums are convergent. And I think I have actually done this part already. So I'm writing such a sum, but now with the correct indices. So we have the pk indexed with the ZD, whereas the elements that I'm adding up in the series in such a space are now labeled from n equal 1 to infinity or so. The main point is just, if you take this H, which is summable at least in the sense of A, so it's a decent continuous function, you can localize the resulting infinite sum. And the localization, the sum of the pieces, here you have a double sum, and you fix the position and you add up over all the contributions is of course the same as the infinite sum in brackets multiplied with psi k. The finiteness is actually a finiteness of this double sum, so you can interchange the order. So for x, every fixed k, so at every place, the sum is absolutely convergent and you can control it, and in this way you get the completeness. Yeah, the next thing is, of course, that if you have infinite sums which are absolutely convergent, then of course, if you ask what is the difference between the infinite sum and the finite approximation. Let's say, what is the error between the infinite sum and the first 100 contributions? And you would say it's the next contributions from 101 to infinity. And that's having a small total sum because the sum of the original one was absolutely convergent. This is an argument that you can use in the atomic situation, whereas if you would work with Pupus, you would say, if I take the sum of the first 100 ones, there are side lobes, and that means that you have to measure with those elements which are used, and then you would have maybe go up to 110. And so this overlap you can save by using this atomic representation. Now, I was adding also that you get a continuous embedding into L1, for example. Well, the compactly supported continuous functions are continuous function with compact support, so they are inside L1, and then you control the norm. So how can you control the norm of such a piece? Well, every such atom has a maximum norm estimate that you can control by the A norm, and then it has a support, and the support is a box or a cube or a ball of finite radius. The little r is depending on how you choose the radius of the psi k. If you would take an atomic decomposition, you would have a capital R, but this doesn't matter. It's the volume of some balls of fixed radius, fixed meaning independent of the index, at different positions. And you know, the volume of a ball doesn't change if you move it around, so you have one constant, and then you have the embedding constant of A into C0, and that's one way to prove continuous embedding in both C0 and L1. Now, the property that I find most interesting or important is the convolution relationship, which I tried to write down in great detail. And it's again going by the pieces. So we take this finite approximation, we take the pieces which have finite sums, and then we compute these things. And for the algebra A, we have assumed that measure convolved with elements from A are in the algebra. We have done this separately for the Fourier algebra, and it's obvious from the very beginning for the C0 space. And we control the support. So two things which are in balls of radius r around I or j are in balls of radius 2r around aj. And therefore we can control not only the A norm, but even the atomic norm. So it's the WAL1 norm. I have also added one theorem, a little theorem, which means that both for the C0 and the Fourier algebra norm, Dirac sequences act in the appropriate way. So you can take the Dirac sequence in L1, and again, we can do it first for standard Dirac sequences, so maybe box functions or triangular functions with compact support. Their supports are shrinking, and you will see that the action of these Dirac sequences now on the A norm will be as you expected. So it's not just the C0 norm, not just the internal multiplication, but now the action of something from L1 or even the bounded measures on the space A. But it's true for both A in the case of the Fourier algebra, and then as a consequence for this. And why? Because if you smooth out the function f, which is living in a ball of radius capital R, then after shrinking this support, everything will be living in a ball of radius r plus 1. And then you use the equivalence of the norm. It doesn't depend on what the radius r is for atomic representation. So you get a slightly different estimation with some other constant, but the decay is like this here. So that's very important. I'm already mentioned that we have this algebra C0L1, which is good for pointwise multiplication even and for convolution, and we will have S0 as another name. It's as for Segal algebra for this space FL1, and maybe also I'm also already stopping at the same place here. I would like to do the proof of the Fourier invariance after the break. So I do a short stop, maybe up to, well, I would suggest to resume after something like 7 or 8 minutes, and resume by doing the more detailed proof of this part here.